to Dror.
Sorry, I forgot to start my own recording. Okay, now it's on. Okay, so here we go. You've read the title and you've seen the abstract. I should only say about what's here, this page, that this is work that continues work of Rosansky, Garofalidis, Kricker, and Ochtsuki, and it's joined with Roland van der Veen of Groningen. The slides and the code within are online at the URL specific written here. And also at the top of every slide, I wish all slides had done that, because I always want to be a page behind or a page ahead, and just slide talks are horrible in that way because things disappear before you manage to digest them. I will also post the video at the same URL, and there is also a paper in progress at web/theta, where web has been defined here. And if you can, please turn your video on. I really want to see you. You're also wonderful. I really want to see you, and I want to see if, Thomas, hello. I want to see if you're smiling or miserable or what. Anyway, happy birthday, Lou. This is, I think, a picture from the first time I met Lou. I don't know if he's here, I don't see him. Back at MSRI in March 1991. So, and unfortunately, I will not come to his talk tomorrow because I'm teaching at exactly the same time. Work was supported by the NSERC and by a grant from the Chu Family Foundation. And I should say that my, the title says strongest genuinely computable. So I better explain what strongest and genuinely computable mean. So first of all, strongest. So the invariant is called theta, and it's really a pair delta, where delta is just the old Alexander polynomial, and something not so new, but newly computable, called theta. And we've computed it on a large number of knots. So for example, if you look at knots with up to 10 crossings, there are 249 of them. And then if you look at Homfli polynomial and Chobanov homology taken together, then they take 248 distinct values on these 249 knots, which means that there is a deficit of 1. If you look at the invariant that I will talk about today, the deficit is 0. And then the tables continue until you come to 15 crossings, which is as far as we've computed, and there are 300,000 knots. The deficit for Homfli and Chovanov is 70,000. The deficit for our invariant, for the invariant I'm going to talk about today, is 6,758, which makes it, at least in some sense, about 10 times better. Okay? I should say that the title of the talk is since 2024, but then I switched it to in 2024 because in 2025, I've added row 2, and row 2 makes it a little bit better. Anyway, what does genuinely computable mean? So genuinely computable means that we can compute it on knots with 300 or even a bit more crossings. And for almost every other knot invariant, when you say 300 crossings, it's science fiction. So maybe you recall Sergei's talk yesterday, and he was talking about 100 crossing knots and the assumption that Moore's law persists for another 100 years. We will be able to compute quantum invariants for 100 crossing knots. Well, 300 crossing knots should take 300 years, according to the same way of thinking. But for us, it takes few hours on a laptop with 0 GPUs. So this, by the way, is the value on the invariant on a random 300 crossing knot, and let me explain this. So you see, the invariant is not only strong and genuinely computable, it's also fun. And let me explain the fun part. So it's really an ordered pair. I think I indicated it before. It's really an ordered pair, the Alexander polynomial and then this theta invariant. The Alexander polynomial is a Laurent polynomial, so you can think of it as a list of coefficients. And then you can draw this list of coefficients as a barcode, where red means positive coefficient and blue means negative coefficient, and the brighter the color is, the bigger the coefficient is. So if you take a 300 crossing knot, roughly, well, that's going to be the Alexander polynomial. Now, if you look at theta, so theta is a two-variable polynomial. So if you look at the coefficients, a two-variable Laurent polynomial. So if you look at the coefficients, you get a two-dimensional array of numbers, which makes a two-dimensional array of blue and red pixels, which makes a picture. So here is the picture for a 300 crossing knot. Now, I should say that there is a little bit of a lie here, because if you draw the picture with orthogonal coordinate system, the hexagon that you see here looks like this, a little bit of a sheared hexagon. So we shear it back again, and it becomes the hexagons that you will see in the picture. Now, if you look at these hexagons, you'll see all sorts of patterns, and I don't understand these patterns. In fact, I don't even fully understand why it's a hexagon. So, so there's a lot of work to do, and I think that's the definition of fun. Okay? Now, here are a few more examples. So these are random knots with 101 to 115 crossings, only the theta part, without the Alexander part. The Alexander part is boring. And, you know, you'll see patterns here. You'll see things that look like diffraction patterns or like sand patterns on a, what is it called, shaking tray. And I have no idea where they're coming from, okay? Here is the Rolfsen table and all the invariants and all the knots in it. Here are a few torus knots, so 13.2, 17.3, 13.5, and 7.6. And finally, here is the torus knot 22/7, which is, of course, an approximation of pi. And again, I don't know what to say. This is what you get. If you like it, good. Okay, I should say that the invariant, oops, sorry, I skipped a slide, is also meaningful. So it gives a genus bound, sometimes different from the Alexander polynomial, so a new genus bound. Strictly speaking, it's unproven, but it's with absolute confidence. So both for theoretical and experimental reasons, there is no doubt the genus bound is really there. And we hope with reason that it also says something about ribbon knots or slice knots. So, but we'll see. Okay, but that's yet to be seen. Okay, let's start with the definitions. So first of all, a convention. T1 and T2 are just variables, and T3 is T1 times T2 for the purpose of this talk. And let me tell you how to compute the invariant. So the first step is a preparation step. So if you have an n-crossing knot, you draw it as an upright diagram. An upright diagram is a diagram in which the incoming strand is facing up. It's a long knot. The incoming strand is facing up. The outgoing edge, sorry, is facing up. all of the crossings are facing up. And of course, you can always draw a diagram like this, because if some crossing is not facing up, you turn it around a bit. Then you mark the diagram with two integers, the edges of the diagram with two integers. So first of all, a running index, 1, 2, 3, 4, 5, 6, and in this case, 7. And then also, so you see, each of the edges is facing up. Sorry, each of the ends of all of the edges is facing up. And so you can measure the rotation number of the edge from its beginning to its end. It starts facing up and it ends facing up, and it's going to do a number of rotations. In our case, all of the rotation numbers are 0, except rotation number 4, which we call phi 4, which is -1, because we rotate clockwise once. Okay? I hope everything is okay so far. So that was the preparation. We'll see where it comes in later. And I want to tell you about something else. I want to tell you about traffic rules for Model T cars. So cars always drive forward on a knot diagram. Okay? So if you have an oriented knot, my knot is oriented, they will always drive forward. When a car crosses over a bridge with high probability, it simply goes, sorry, I should have said it differently. When a car goes under a bridge, with probability 1, it just goes through. So when it goes under a crossing, with probability 1, it goes through. But when it goes on the over edge of a bridge, with probability close to 1, namely with probability t to the s, where s is the sign of the crossing, it goes through, and with the complementary probability, it drops down to the lower strand, as you see in this picture here. Now you can complain that t to the 1 and t to the -1 are not probabilities at the same time. And indeed, I don't really mean probabilities. These are algebraic probabilities. I use the rules of probability for addition and multiplication, but I don't interpret these probabilities as frequencies, as numbers between 0 and 1. At the very end of the knot, all cars fall off a cliff and disappear. So here is a summary. If a car enters here, if you inject car traffic here on a positive cross sign knot, and you put a traffic counter, so this little edge here is a traffic counter, a thing that measures how much traffic goes through, looks like this on the highways. If you put a traffic counter on this edge, it will measure traffic T. And if you put a traffic counter on this edge, it will measure amount of traffic 1 minus T. If you inject the traffic here, then this counter will measure 0, and this one will measure 1. And likewise for the negative crossings, except with T replaced by T inverse. Are you still with me? People whose face I see say yes or no, wave, or you know. Okay, good. So here's a definition and example. So the traffic function, also called sometimes the green function or the 2-point function, it's a matrix whose entries are G alpha beta, and it's defined as follows. So alpha is an edge and beta is an edge. And basically what you do is you inject traffic on edge alpha and you measure how much traffic you see on edge beta. And with the convention that if alpha is equal to beta, then the injection point is before the place where you measure. Okay? So, oh, hello, Hans. Here's an example. So let's take the simplest node diagram I can think of, which is non-trivial, so the kink, okay? And if I inject traffic on edge number 1 and measure on edge number 1, the measurement measures 1. If I inject traffic on edge number 1 but measure on edge number 2, what am I going to measure? So first of all, every car that gets injected goes under the crossing and comes here. So I see 1. Then some of the cars fall and I see them a second time. So I see 1 minus t. But then of the cars that fell down, right? So some cars fall once and then some car falls twice. And the ones that fall twice add to the measurement 1 minus t squared, and so on. So basically, cars are going to go around a number of times, and I'm going to get that the overall measurement is sum of 1 minus t to the power p. And this is a geometric series whose sum is t inverse. So the measurement that this traffic counter will see is t inverse. And finally, all of the cars eventually go to edge number 3, but only once. If you go through to edge number 3, then after that you fall down and disappear. So edge number 3, the counter on edge number 3 will measure an amount of traffic equal to 1. And then you repeat this calculation if the injection point is edge number 2, and then on edge number 1, you'll see nothing because no car will ever go back to the past. On edge number 2, you'll see the same amount as before, and edge number 3, same amount as before. And if you inject the traffic on edge number 3, then here and here you'll see 0, but on edge number 3, you'll see 1. And so the traffic function or the green function or the 2-point function for a kink is 1 t inverse 1. So 1 t inverse 1, 0 t inverse 1, 0, 0, 1, and here it is. Am I still good? Good. Ooh, you know, there has to be something horrible at some point. Given crossings C, so my notation for a crossing is a triple of integers. So S is the sign of the crossing, I is the index of the incoming upper edge, and J the index of the incoming lower edge. So given 3 crossings, C, C0, and C1, I define 2 functions. A function f1 of C is this horrible combination of traffic functions. I will explain it a little more on the next slide. But notice that it's horrible in the sense that it has 18 terms. But you know, if you're a computer, you don't care. 18 is a small constant, okay? So bad news for this invariant is that, yes, it's genuinely computable, but only if you're a machine, okay? The other point is that it's quadratic in the green function, and oh my God, I forgot to, I missed one slide. So, sorry, that's a mistake. Really, I should have said that there are model T-nu traffic functions called G-nu, whose entries are G-nu alpha beta, where nu is 1, 2, 3. So basically, if you compute G, you replace T by T sub nu, so T1 or T2 or T3. So these functions here are indicate also the value of nu. So this is a function of T3 multiplied by T2, whatever, some funny polynomial. What you get is some funny combination of the G1, G2, and G3 traffic functions. Similarly, there is a function F2 that depends on two crossings, and it's actually a bit simpler, but it's cubic in the G's as opposed to quadratic for the previous one. And then there is also a correction term that has to do with the rotation numbers, and it's defined here. And I'm not going to say more about it because it's only a 45-minute talk. And now comes the main theorem. So the following is a knot invariant. So theta of a diagram defined to be delta 1, delta 2, delta 3, I will define these later, times a sum over the crossing of F1 of the crossing, plus a sum over pairs of crossings, C0 and C1, of F2 of C0 and C1, plus this normalization, which I will skip, this correction, which I will skip. And I think I want to make two comments. So comment number one is, if you know the traffic function, once you know the traffic function, these things are trivial to compute. This is a linear amount of summands, and each summand is maybe 14 or 18 terms, but that's still trivial for a computer. And this is a double sum over the knot, which again, it's a quadratic amount of work. So computing theta of D is extremely simple from a computer perspective. Once you have the traffic function. And the second point that I want to make is that if you look at what F2 measures, F2 is a sum over pairs of crossings. So here is crossing number 1, here is crossing number 2, and you sum over all pairs of crossings in your diagram. And for each pair of crossing, you take some contribution, which is quadratic in which is a product of traffic functions, where one traffic function is for model 1, model T1 cars, another one for model T3 cars, and another one for model T2 cars. So really, it turns out that you're measuring basically processes in which model T3 cars starts in the vicinity of crossing number 0, goes to the vicinity of crossing number 1, breaks up into a model T1 and a model T2 car, and these two go back to near crossing number 0, and you figure out what's the amplitude of this happening. So this is somehow a physicsy interpretation of this formula. And if these pictures remind you of Feynman diagrams, it is because they are Feynman diagrams, but I'm not going to tell you the details of that. Yeah, this is the end. This is the definition of the invariant. Okay? But you know, it's a theorem, so I should start proving it. I'm not sure if I will finish the proof, but here is the beginning. So claim number 1 is that the traffic function is what I like to call relative invariant. Namely, if you want to measure the amount of traffic from, if you inject traffic on edge number alpha, and you want to measure the traffic in edge beta, then I claim that this amount of traffic from, you know, if you have a big node diagram, I claim that the amount of traffic from one place to another, if you inject traffic here and measure it here, the amount of traffic is independent of Reidemeister moves that you may make somewhere else. So if you make Reidemeister move around here, it's not going to change the traffic from here to here. Okay? And roughly here is the proof. So you just have to test it for the 3 Reidemeister moves, and I'll start from Reidemeister 3. And basically, if you inject the traffic on the bottom left, on the left-hand side of the Reidemeister move, you want to compare it with injecting traffic on the bottom left, on the right-hand side of the Reidemeister move. But you see, if you inject traffic here, then with probability t it gets here, and with probability 1 minus t it gets here. Those cars that got here with probability t will come here, so you'll see on the output here a t squared amount of traffic, and down here you will see t times 1 minus t because you had to drop down. And if you do the same computation for the right-hand side, it's a little bit more complicated, but the answer is the same. So if you inject the traffic here, you can fall down to here and you'll get here with probability 1 minus t, and then you can fall down again and you'll get 1 minus t squared traffic from here. But there is a second route that goes to the top left, namely, you could have come through, this happens with probability t, then drop down, this happens with probability 1 minus t, so you'll come here with probability t times 1 minus t overall, and then you're going under, so you're undisturbed, so the contribution is t plus 1 minus t, and then if you look at the sum of these two terms, it's exactly equal to this. And the moral is, and you do the same for the other inputs and the other outputs. And in fact, if you've ever checked that the Bureau representation is a representation, this is exactly the check. But anyway, the conclusion is that if you enter a Reidemeister 3 interchange, you're going to exit with the same distribution, whether you're doing the Reidemeister 3 left or the Reidemeister 3 right, and that exactly proves that statement. Similar things apply for Reidemeister 1 and Reidemeister 3, but I will not show you. Okay? So that was lemma number 1. So the traffic functions are somehow related to the knot. Somehow see knot theory. That's the first thing to see. And the second thing to see is that the traffic functions satisfy what I call the G rules. So if you are near a crossing C, whose sign is S and incoming strand I incoming upper strand I and incoming lower strand J, and just for short, I will indicate the edge after J with J plus and the edge after I with I plus, then Gj beta is equal to Gj plus beta plus a delta function. Gi beta is equal to T to the S Gi plus beta plus some other contribution plus a delta function. What are these rules? These rules are just an algebraization of the traffic rules that I've indicated before. You see, if you enter a crossing on the lower strand in position J, and you then sorry, I want to say it. Yeah, sorry. If you inject traffic here, all the traffic that you see will go to here. So injecting traffic at J is the same as injecting traffic at J plus 1. Hence, Gj beta is equal to Gj plus beta. The only exception is if you measure the traffic right here. Then traffic injected at J will get counted, but traffic injected at J plus 1 will not get counted down here. So that's this delta function. Likewise, if you inject traffic at I, then that's the same as T times injecting the traffic at I plus 1 minus T times injecting the function at J plus a delta function. And then there are similar rules for moving the traffic counters, but we don't really need them right now. But the moral is, so I just told you the lemma, and I essentially also told you how to prove it. But the corollary is that the traffic function is easily computable. Because if you look at these equations, they really mean that the traffic function G satisfies A times G is equal to the identity, where A is a very easy to specify matrix. Here is the matrix. Basically, it's the matrix, it's a 2n plus 1 by 2n plus 1 matrix, where you start with the identity matrix, and for each crossing Sij, you add a contribution in row I and row J and column I plus and column J plus, you add a contribution which looks a little bit like the Bureau representation. So for example, here is crossing, one of the crossings of the trefoil. It's a crossing where I is equal to 3 and J is equal to 6. So the matrix A in row 3 and row 6 and column 4 and column, 7 will have a copy of the Bureau matrix. So the moral we have is that A times G is equal to the identity, where A is something simple, and therefore G is equal to, maybe I should have written this in advance, and therefore G is equal to A inverse, and that's easy to compute. So inverting a matrix is polynomial time. It's way easier than computing a state sum. Maybe when you are undergrads, you hate it. And even when you're grown-ups, you will never do it for a 7 by 7 matrix. But if you're a computer, you don't care, and you can do it for 300 by 300 matrices. Okay? So that actually concludes explaining why computing the invariant is easy, why this is a genuinely computable invariant. Everything is polynomial time. All you have to do is invert a matrix once, and then compute a certain sum over the knot, and then a second double sum over the knot, and both of these activities are easy. So that concludes why the invariant is easy to compute. Oh, by the way, for the trefoil knot, this is the traffic functions that you get. And maybe I should also note that the matrix A that we got is one of the standard presentation matrix for the Alexander module of the knot, and therefore its determinant up to some silly normalization is the Alexander polynomial, and that also explains the normalization factors in the formula. They're there basically to kill the denominators. If you multiply by determinants, you kill the denominators that occur in inverses. So that explains the normalization factors, but it also explains why I like to think of the invariant as a pair, delta theta, and this is because delta is a part of the computation anyway. first part of computing theta is to compute the Alexander polynomial anyway. Okay. Okay. Second corollary of the G rules is that proving invariance is easy. I think I want to rush through this. The basic point is you need to compute the sum of traffic functions corresponding to the left-hand side and the right-hand side of a Reidemeister move. Well, if your summands are away from the move, so if the two crossings C0 and C1, say, are away, then by the relative invariance of the traffic function, you get the same contribution on the left as on the right. So that's not interesting. So the only interesting case is if one of the crossings is one of those. And in this case, the traffic functions do change. The G nu alpha beta do change. However, we have rules that allows us to move G alpha beta, where alpha and beta are evaluated inside the move, to G alpha beta, where alpha beta are pushed up, where alpha and beta are pushed up using the G rules. And when I push them up, they are the same. Because they go outside of the move, and then they are the same on the left and on the right. So all I have to do is to compute a finite sum corresponding to whatever happens here and whatever happens here, apply to it the G rules, and if I get the same answer, I've proven invariance. I know this was vague. I'm not going to do it in full detail. Also, you know, at the end of the day, this is a summation over several things, and my things have 18 terms. So my contributions have 18 terms in it, so it's way over my IQ. So I delegate it to a computer. So I write a little computer program in which, you know, I define T3 to be T1 times T2, and then I define F1 and F2 and F3 as before, and then here are the G rules. If you look at this very carefully, you'll see that it's exactly the G rules that I've mentioned before, and then here is the summation corresponding to Reidemeister 3 left and Reidemeister 3 right. I look at it down here, and then I ask my computer if left-hand side is equal to right-hand side. The computer says true, and that's a proof of invariance under Reidemeister 3. Again, I've gone through it really quickly, but it is a proof. Okay? But you see, now I can just implement the invariance. So here is the main program that compute the invariance. So basically, I determine the crossing and the rotation numbers using a program that I call ROT. That's not really a part of the business. It's the preparation thing. So I'm not showing you how it's written. It's not. It's a linear time program. It's really not interesting. Then I let A be the 2n plus 1 by 2n plus 1 identity matrix. For each case within the list of the crossings of a crossing Sij, I add to A in row I and row J and column I plus 1 and column J plus 1 the block that I've suggested before. I let delta be the determinant of A. I let G be the inverse of A. I don't want to talk about technicalities, and I let theta be the single sum of before plus the double sum of before plus the correction term, which I'm not listing, and then I output delta, and then delta with some changes of variables multiplied by theta, and that's all. This is the full program. This computes theta from the beginning to the end, and we do it for nodes with 300 crossings. So here are a few examples. So theta of the trefoil node comes out to be, well, this is the Alexander polynomial, and then the lowercase theta contribution, and the Alexander polynomial is just positive. So this corresponds to 1 over t. This corresponds to -1, and this corresponds to t. And the two variable part becomes this lovely hexagon. And for example, the t1 squared, t2 squared is, I think it's this contribution here. Remember that I was shearing stuff. So yes, I think it's this contribution. And it's negative, so this is the -1, the color blue. Here are the Conway and Kinoshita-Terasaka notes. And well, first of all, note that the invariants are first of all, note that the Alexander polynomials are trivial. And note that the invariants are different. So theta detects mutation. Also note that the genus of the Conway polynomial seems to be bigger because you see theta is a genus bound, and this here is a higher degree polynomial than this polynomial here. And that actually matches with what we know about Conway and Kinoshita-Terasaka. Here again are the torus notes, and I'm near the end. Any comments so far while I'm having tea? Sorry for being so quick about it. Oh, somebody wrote something on the chat. Should I be looking at this, or is it... I have to come closer to the screen. I think that the... Okay, so question is, you know what? I'll wait with these for the end of the talk. Okay. They're not immediate clarifications. Anyway, I do have a good number of questions and conjectures and dreams. So first of all, just disclosure, there is a reasonably similar invariant by Garofalidis and Kashayev, which takes exponential time to compute, but otherwise has similar properties. We expect that it's not the same, but we do expect that there will be some relationship. So question to you, figure it out. Okay. On classical notes, sorry, theta actually extends to virtual notes or to rotational virtual notes. But on classical notes, theta always has a hexagonal symmetry. We actually don't know how to prove it. We expected it ahead because it came from some theoretical place, and I didn't yet tell you what this theoretical place is. We expected it, but we cannot prove it from the formulas, directly from the formulas we have. Here is the theory place it came from. And people might have heard me talk about it before, and there are references. For example, I think this is a talk that I gave in Vietnam 6 years ago, just before COVID, which summarized this, but we still didn't have the good formulas. We only had the theory at the time. And the talk is on video, so you can watch it. But the basic point is that semi-simple Lie algebras are in some sense the double of their upper Borel subalgebras. So the dual of the upper Borel subalgebra is the lower Borel subalgebra, and the lower Borel subalgebra has a bracket, therefore the upper Borel subalgebra has a co-bracket. So if you know the Borel subalgebra, its bracket and its co-bracket, you can recover the semi-simple algebra. But in fact, you can do something sneaky and multiply the co-bracket by epsilon, and then you get a one-parameter family of Lie algebra. So you get a one-parameter family, which you could call G sub epsilon. And for epsilon not equal to 0, it's the usual semi-simple algebra you started from. For epsilon equal to 0, it becomes the upper Borel semi-direct product, the lower Borel, which is a much simpler Lie algebra. And what you do is you apply the whole quantization machinery and quantum invariance machine to G epsilon instead of to G, but you don't aim to compute the G epsilon results, you aim to compute the power series expansion of that as a power series in epsilon. At epsilon equals to 0, you have a solvable algebra to manage, and the computation comes out easy. And if you look at epsilon to the power 1, you get, and in fact at SL3, you get the formulas I wrote. If you look at epsilon, okay, sorry. But I should say that all of this I knew, Roland and I knew for many years, and but in fact, what we really did was, out of this theory, we figured out what the shape of theta should be, what roughly the formulas should look like, and then we use undetermined coefficients to find the specific coefficients of the polynomials f1, f2, f3 that I've indicated. And this is because tracing the theory into concrete formulas was just too hard. So we just figured out the shape of the output and then solved for what the output should, what the invariant should really be. So strictly speaking, we don't know that the theory matches with the invariant that I defined before. So strictly speaking, this is a conjecture. Next, likewise, theta is probably related to the two-loop contribution to the Kontsievich integral, whatever it is, and that was studied by Garofolidis, Rosansky, Kricker, and also in great detail by Ochtsuki. But again, we know it's related, but strictly speaking, we don't have a proof. Next, there were Feynman diagrams in the business at some point, and in fact, theta really does have a QFT formula, a zero-dimensional QFT formula, in which you integrate over a space which is 6 times the dimension of the space of edges. There are I'm skipping because I'm running out of time, but there are very, very good reasons to think that there should also be another perturbed Gaussian integral formula for theta, where the integration is happening on a space which is 6 times the first homology of a ciphered surface of the knot. Roughly speaking, the Alexander polynomial is a determinant of something that's evaluated, that's computed from on H1 of sigma, and that's the same as a Gaussian integral over H1 of sigma. So over 2 copies of H1 of sigma, as it turns out to be. So theta should be a multiple integral over the same. And if that were to be true, that would explain the genus bound, which, as I said, is absolutely solid. There is no chance that it's wrong. And that seems to be the only reasonable explanation for it. There should be a direct quantum field theory reduction of Chern-Simons to theta, and I'm telling you here roughly what it should be, but I don't have time to elucidate. I should say that there is nothing special about SL3 and epsilon to the power 1. There should be other Lie algebras and higher powers of theta, but really, I don't think that these invariants at the end will be explained by Lie algebras. I think Lie algebras are a red herring. They really shouldn't be in knot theory. So I think whatever we're doing is going to come out more natural. And the last dream is that we will have something to say about ribonauts. And thank you for listening. I'm
Thank
done.
you. Thank you. Great talk. Thank you.
Thank you for turning the video on.
Yeah.
So